Next up, we've got a man who was voted the best hair in Ethereum, a self-professed curry enthusiast, and a builder at Celo. We've got the one and only James Prestwich joining us today. Awesome. Well, thanks for joining us today, James. Really excited to hear your talk. Whoa, we've got some animations and everything.
I joined Celo and they gave me this whole brand package with animated GIFs and icons and, the whole 9 yards. It's not so bad.
We'll take it away and we'll talk to you in a little bit. Thanks, James.
Perfect. Thanks, Aiden. Hey, my name is James Prestwich. I work on protocol at Celo, and a lot of what I do is bike shedding consensus systems. So I've implemented Bitcoin transactions in 6 different languages and a bunch of Ethereum library stuff. Mostly what I work on is cross-chain communication, and that requires a very deep technical understanding of both chains that you're working on. In my spare time, I got a degree in Japanese literature and have never given that up, even though it's not a huge part of my day-to-day work experience right now. Maybe I'll get back to that pretty soon. The goals for this talk is to give an intuitive understanding of these technical systems we call bridges, what they do, what they're for, and then segue into my favorite topic, which is the communication methods that underlie them. And to give a brief overview of how those work, and then go on to categorize existing work in this framework. So the idea here isn't to tell you about a product or pitch you on something. We're just going to try to do some first principles about bridges and cross-chain communication. So this is kind of the idea behind a bridge, right? Is we have some Bitcoin, we lock it up, something happens that causes tokens to be minted, and then you go use them in your dApps. And when you want your Bitcoin back, you just do it all in reverse. So I just mirrored the graph from the last slide and used it again. It's a cheap way to just get more slides into the presentation, take up a little bit of time. Okay, so what makes it a bridge? From these 2 graphs, what makes the bridge? It's this part, right? It's the minting and the burning. You have this supply consistency of WBTC that should be backed by locked Bitcoin, and TBTC works the same way. But what is actually the hard part is this bit, the magic that happens behind the scenes that the user is never really aware of. And so if we want to unpack that a little bit, what you actually have in there is 2 one-way communication channels. You have a message system that goes from Bitcoin to Ethereum, and one that goes from Ethereum back to Bitcoin. And all of the complexity of the bridge application is in establishing these dual simplex channels. Dual simplex is a complicated way of saying that these are 2 independent, so they're dual, and they're simplex, they're one-way communication. We use these dual simplex communication channels to make what we call full duplex, where you can send messages back and forth. This is all trying to make an analogy to traditional telecoms. So we're using these 2 channels to establish the application, the bridge, what we actually want, minting and burning these Bitcoin tokens. But the bridge is a relatively small piece of the complexity. So I want to dig a little deeper into how communication works. More brand assets. We get this fancy confetti slide. We are sending messages from one chain to another. There's no way to know if the response is received. You're not going to get a message back on the same channel. So how do we actually send those with confidence that they're going to get there? What we would like to do, what we wish would happen, is that the Bitcoin and the Ethereum chains just talk to each other and nothing happens and it just works, right? Unfortunately, in reality, things are a bit more complicated. We have these trust boundaries. Bitcoin can't know what's going on off-chain. Ethereum can't know what's going on off-chain. Ethereum doesn't know about Bitcoin. Bitcoin doesn't know about Ethereum. We have to figure out some way to get the message across these boundaries. And we have to, because this is a trust boundary between the outside world and Ethereum, Ethereum can't validate incoming messages. It can't establish the truth of those without some very specific logic. So you can't just have the message go straight to the DApp, right? We have to insert some amount of processing into this to make it work. The DApp needs to know that the message is good. So now, we've gone from just a message sent from Bitcoin to Ethereum. We've introduced new steps. We have to dispatch it on the Bitcoin side, and then we have to process it on the Ethereum side. And we have to determine if that message is any good. If you're familiar with flowcharts, you're going to know that these parallelograms are input-output from a process, and the diamond is a decision point. Normally, a diamond would have 2 whiskers coming out from it, but for convenience and because I'm really lazy, anytime you see a diamond with only 1 whisker, just assume that the other path is the message is discarded and you do not communicate between chains today. So if you get a bad message, we're just going to throw it away. All right. So we want the Bitcoin chain to dispatch this Ethereum transaction, right? But it can't actually do that. Bitcoin doesn't have SecP keys. It doesn't know what an Ethereum transaction is, and it can't sign things or use smart contracts in any way, really. So we have to come up with some other system that's going to dispatch that transaction for us. And so we insert these new off-chain actors. Bitcoin is going to commit to some message that needs to be sent. It may not know where that message is going. It just knows that it has produced a message and committed it to the chain. Some off-chain actor is going to see that, decide whether or not they want to forward it, and if they do, dispatch an Ethereum transaction. And then on the Ethereum chain, we get that transaction, we start processing it, we see if the message is any good according to some definition of good. And if it is, we send it on to the DApp. If the off-chain actor doesn't see the message, chooses not to forward it, or if the message is no good, your message gets discarded and there is no communication between chains today, and you do not get a bridge today. Right. So the core problem here is that chains are passive, right? They only respond to things that are coming in. You send a transaction, it triggers some series of on-chain events, and the chain updates its state. The only outcome of a transaction in a blockchain is updating the chain state. It can never autonomously trigger other actions, which is what we want it to do. Communications have to be active, right? You have to send the message, you have to know that it gets there, and you have to have some sort of expected response to it coming back through another channel. So in order to make the communication system active, we need these off-chain actors that are observing chain state and forwarding messages to the other chain. And they must be spending Ether on TX fees to do this. So we've talked a bit about, what is good. The Ethereum chain has to know this incoming message is good if it wants to act on it, right? So let's zoom in here on the destination chain. And we rotate it sideways so I can make this bigger and see it in one slide. And the majority of the communication channel design, the majority of the bridge effort and complexity is in what makes a message good. When Ethereum sees this message that is ostensibly from the other chain that's been forwarded by an unknown off-chain actor for unknown purposes, how does Ethereum check that that message is trustworthy? Or in more concrete terms, how does it check that the message is actionable? At some point, the destination chain receiving the message has to commit. It has to say, yes, this is valid, and I will update my state as a result of this message being processed. We need to set, concrete, deterministic criteria, usually in Solidity, for how you do this. Okay, so we have a few different trust models for this. The simplest one is proof of authority. So in this example, I will sign every message Bitcoin sends, and I promise that I will do it correctly. And Ethereum can just check that these messages are signed by my keys. I think this is a great system. It's perfectly trustworthy because I trust myself perfectly. And so, this is supposed to say James instead of relay. We'll just pretend it says James there. So in a proof of authority setting, messages are small and can be arbitrary. I can sign anything. You know, I'm me. I decide what I can sign. And I can update that at any time. And they're fast and cheap to validate. The downsides are that there's a single point of failure. If I get hit by a car tomorrow, then James BTC is not going to be worth very much. Centralized points of failure are very censorship prone. And if, you know, like I decide to run off with all the Bitcoin, there's nothing you can really do about it. So the failure mode is terrible. You know, these are easy to extend into a federation where it's like six different people or 7 signers, you know, in charge of these things. You have the Liquid Federation and the XDAI Federation and all these other kind of federated systems. But they're still trusted. They're still censorship prone, and there's still no recourse if the federation decides to steal your money. So we'd like to do better than that. And so one of the like intermediate solutions that's pretty good we came up with is stateless SPV. And what we're looking for here is not did James sign this message, it's someone is sending me a message. How much money did they spend to produce it? How costly is that message? I know, you know, as a verifier, as the Ethereum blockchain, that if somebody spent $2 million creating a message, it must be pretty important to them. And I can probably trust it up to $1 million or so. The nice thing here is that Bitcoin and other chains with proof of work are creating that costliness for you all the time. And so the verification for this is very simple. You check that the message is syntactically correct, and then you check that there's a lot of proof of work on top of it. How much proof of work there is a security parameter that's adjustable. Essentially, all you're doing here is checking that somebody spent millions of dollars of electricity to produce this message. And if they did, it's good. And we can validate that message and forward it onto the DApp. We can decide to commit it to the chain state and the destination chain. So stateless SPV is really nice in some ways. It's small. It's no ongoing process. That's why we call it stateless, is it needs no outside information. And anyone can participate. Unlike proof of authority or federations, anyone can construct this SPV proof from Bitcoin, can go get those Bitcoin headers with the transaction in it. The cons is that it's proof of work only. It relies on this unforgeable costliness, the objective costliness that proof of work has and proof of stake doesn't. And in practice, because people have selected these really, really terrible proof of work algorithms like ETH-hash, it only works for Bitcoin, which has a reasonable, commonly used hash function for proof of work. So stateless SPV has this extremely narrow scope. It can only do one-way communication from Bitcoin to some other chain. And that makes it not very useful for the vast majority of bridges. And stateless SPV does permit forgery by wealthy adversaries. So you have to carefully parameterize your costliness requirement to ensure that it's high enough that it can't be forged, but low enough that it's cheap to verify. And that's a very delicate balancing act. And so the last method, model of communication that we're going to talk about is relayed SPV. So this is essentially the destination chain is implementing the sending chain's consensus process. You may have noticed that I talked a lot about proof of work in stateless SPV. It's because proof of work is Bitcoin's consensus process. It's how you decide what is true in Bitcoin. Relayed SPV is not just we're going to check for costliness through proof of work, it's that we are going to maintain actively in the Ethereum chain state, in the destination chain state, a model of the remote consensus process on an ongoing basis. So we actually have to bifurcate our processing here a bit, because we need this local view of the remote chain, and we need to update it and keep it up to date. For proof of work, this means tracking the latest block header. We get a new message. If it's a header, we're going to try to add it to our local view of the Bitcoin chain. If it extends a known header, if it is extending our local view, we're going to check the proof of work, and then we're going to update that local view. So that way, you have the Ethereum chain running a Bitcoin-like client actively. It's following along the chain tip, it's processing new headers, it's checking proof of work, whole 9 yards. And for regular messages, you're going to check if they're in the local view of the remote consensus. So you keep your local model of Bitcoin and you check if a specific transaction is confirmed in that local model. Then you can check if it contains a message and dispatch that message to the dApp. The validity here is coming from the actual consensus process of the remote chain. And this works for Bitcoin, for proof of stake systems, but not for non-Bitcoin proof of work systems for the same reason Stateless SPV doesn't, because they've all chosen very bad proof of work algorithms. Okay, so we're going to maintain this relay where all the headers from the remote chain are getting relayed over to the destination. And we're going to keep a local model of the sending chain state where we can validate that messages were in fact sent. And we do that by running a light client that anybody can update. All right, so the pros here are, it's as good as the remote consensus is. If the remote miners or the remote validators, stakers, are honest, this relay will always produce correct results. If they're dishonest, it can produce incorrect results. And anyone can participate because the remote chain and its consensus are public information. And we get this really nifty thing for modern proof of stake systems where you get logarithmic complexity. I only need to process like this one header out of every 100 or a logarithmic number of headers for modern proof of stake systems. And there are very complex reasons for why that is, but it makes it extremely cheap to process. The downside, though, is we have all of this overhead, right? We're sending messages for some number of block headers. Those messages are expensive to process because you have to do a bunch of signatures for proof of stake, or you have to do a bunch of work for proof of work. And it relies on a trusted setup. So you have to kind of insert known good state, like a genesis block for the relay. And while you're maintaining it, if you fall behind, you'll need to redo that trusted setup for any proof of stake chain. This is a consequence of the kind of subjective epoch-based proof of stake consensus. But essentially, anytime you go over a certain number of blocks without processing a new message, you lose your trust in the remote consensus process. You need to update your relay. For Celo, it's once a day. For ETH2, it'll be every epoch, which is 12 minutes, I think. So you need to keep your relay up to date extremely often, or you lose the ability to validate messages correctly. All right. So while we're on the subject, what's sharding? We're expecting ETH2 to launch with shards. Those shards eventually will be able to communicate between each other. If we've established that there are 3 ways to communicate between chains, how does sharding work? Sharding is kind of what we call mandatory relayed SPV. So when you put this relay tracking the remote chain state into the consensus process instead of into the state. So if part of Ethereum's block header validation was that it had valid Bitcoin headers in it, that would be sharding rather than a relay. Typically in a sharded system, you get recovery from failures. So if we commit some invalid Bitcoin message, we would roll back to take that message out of the destination chain. And in ETH2, if an invalid transaction is committed in one of the shards, the beacon chain and the other shards will roll back to fix that and omit it from the history. So sharding is a kind of relayed SPV with failure detection and recovery. All right, and while we're talking about communication models, what about atomic swaps? To which I answer, what about them? Nobody likes them. Please stop asking. Okay, so we've got through the models section of the talk. I'm going to review the Q&A real quick before going into the last slide that I have. So let's see, are any of these applicable and would clarify things right now? What improvements would I like to see in these networks to get to the ideal situation where communication is almost native? Sorry, Aiden, I'm trying to clear up any outstanding questions about models, and then I go into the last 5 minutes.
Okay, understood. Yeah, cool. Sounds good.
Cool. Yeah. So as far as improvements go, I've insulted people's proof of work choices a few times throughout the talk for very good reason. All of the proof of work chains with memory hard algorithms essentially cannot ever participate in these cross-chain systems, in relays, bridges, any sort of cross-chain application except via atomic swaps. So just right off the bat, I would get rid of all of those. And then for proof of stake systems, I think the key thing is that you need to be able to check the hash and signature algorithm of the remote chain. And everybody is using a bunch of different signature algorithms right now. BLS 12381, 12377, ED DSA, and a bunch of kind of unrelated things. So it would be nice if there were a standard that everybody followed there. Anyway, so getting out of models, I want to briefly touch on classification of existing systems. I just put together a little chart with most of the major ones that are out there in the wild right now. Running down the list, you have WBTC and RenBTC, where things are held in multisig by the company that runs it. So you get this kind of trusted federation with a small number of signers. For TBTC, we have stateless SPV, and it allows us to do a bonded federation on the round trip, the way back. Essentially, we're cheating by using the same one-way communication channel twice by verifying that the return trip completed successfully and penalizing people if it didn't. So rather than sending a message and then sending one back, TBTC sends two one-way messages. First is setup, and the other is did teardown work. If teardown didn't work, the signers get penalized. Cosmos IBC is going to be the first fully relayed SPV bridge between proof-of-stake blockchains. They've been working on this for at least 3 years now, and it's finally going to be included in the hub chain. Rainbow Bridge is Near's recent entry into this. It relays Ethereum onto, I have an error here. It should be relayed on both sides there. Rainbow Bridge relays Ethereum into Near and Near into Ethereum using optimistic fraud proofs. So the Near relay is somewhere between a bonded federation and a full relayed SPV. It has signers that are expected to do the work, but the signers are penalized by fraud proof if anything goes wrong. Solana's wormhole is currently in fully trusted, but will eventually move to the same model as Rainbow Bridge, if you believe their plans for it. XDAI, the POA network, is fully trusted federation. They're looking to move towards an open federation. And lastly, we have ETH2 deposit contract, which is just a trusted federation right now. There's no actual consensus level communication happening between ETH1 and ETH2. You have the open dynamic federation of ETH2 validators who are trusted to issue new deposits when ETH1 is moved. And you may notice I'm speaking at CSCON, but I haven't brought up Chainbridge in this classification. I have always seen Chainbridge as more of a scaffold and framework for building these things. It can be extended to work with any of these communication models. The goal of Chainbridge, in my view, is to provide a shared common foundation for the off-chain actions that communicate between chains. And I think that's really cool and useful. Anyway, that's the end of my slides. I'm going to leave up the classification slide, which I have unhelpfully titled terminology.
Well, thank you so much for that, James. As always, incredibly informative, and I really appreciate the way you've classified Chainbridge, because I don't think people necessarily understand that. So I just really appreciate how you've approached this, and also just the educational aspect of all of this, because yeah, most people really don't, and probably still, unfortunately, will not understand a lot here, but at least know where to go to start to understand these things. So I really appreciate you taking the time to really cover all of this, because it's incredibly important, especially as we're moving towards a world that will need all of these different tools. So thank you so much for this talk. And you've gotten a good hang of the Q&A section. So we got one more question for you, I'm sure you've seen, which is, what are the challenges of creating a test suite for covering all the edge cases for determining if a message is good?
Yeah, this is a very good question, especially when it comes to Bitcoin, where most of my work has been. Bitcoin does not have a specification. Instead, it has a C++ client that you have to go and read and or run to see what happens. So there's a huge number of challenges, because we had to essentially develop from scratch a large corpus of test cases to check that our implementations conform to Bitcoin behavior. And it was really painful and unpleasant. This gets much easier in Ethereum and ETH2, where specifications are more common and more in-depth. It is much easier to implement an ETH2 light client than a Bitcoin light client, because everything you need is right there in one document. Of course, it's also easier because ETH2 doesn't do anything right now, but that's a conversation for another day.
Well, that is quite the hot take to leave us on. I know many disagree with that statement, and maybe a few will agree. So we're going to maybe keep it at that, and maybe we'll slot you in for 2 talks next year, one on bridging and then one on Ethereum hot takes, where we just scroll through your Twitter.
Oh, actually, that sounds like a really good session.
So James, I just want to say thank you so much for joining us. Congratulations on the new work that you're doing and everything that you've been doing. And we're really excited to see how our work together can continue to evolve as we're bridging Celo to Celo in what is, I think, a really incredibly exciting way. So hopefully more can come out to the community soon about that.
Yeah, I definitely agree. Thanks so much, Aiden.
Thank you, James.